Far beyond the glittering spiral arms of the Milky Way, deep in the direction of the constellation Sagittarius, an invisible colossus lies buried beneath clouds of interstellar dust. Sagittarius A-star, the supermassive black hole at the galaxy's core, dominates its surroundings with a gravity so powerful that not even light can escape once it crosses the boundary known as the event horizon. From Earth, it is roughly 26,700 light-years away, so distant that its scale is almost impossible to imagine. Yet, despite its remoteness, the black hole's influence extends across the galactic center, shaping the orbits of thousands of stars and sculpting the Milky Way's very architecture. What if a force at the heart of our galaxy shaped everything we know? Join us as we uncover the mysteries of Sagittarius A, the supermassive black hole that holds the Milky Way together. The discovery of Sagittarius A-star began in 1974 when astronomers Bruce Ballack and Robert Brown, using the National Radio Astronomy Observatory's interferometer in Green Bank, West Virginia, detected an unusually bright and compact radio source in the middle of the Milky Way. Brown named it Sagittarius A-star, the asterisk marking it as an exceptional and energetic object. For decades afterward, no telescope could reveal what it was. The galactic center is veiled by thick clouds of gas and dust that block visible light, leaving scientists to rely on radio and infrared observations. What they saw was an area of tremendous energy, but no visible object to account for it. An invisible gravitational monster seemed to be lurking there. By the 1990 seconds, technological leaps in infrared astronomy allowed astronomers to track the motion of stars in this crowded region. Using the European Southern Observatory's New Technology Telescope in Chile and later the Keck Observatory in Hawaii, researchers began to observe stars whipping around an unseen point at incredible speeds. One star, S2, became the key piece of evidence. It orbits the invisible center once every 16 years and, during its closest pass, races through space at more than 25 million kilometers per hour. From its orbit, scientists calculated that the central object must have a mass of around 4.3 million suns, all packed into a space smaller than the orbit of Mercury, about 44 million kilometers across. No known object, except a black hole, could possess such immense density. Although Sagittarius A-star is massive, it is surprisingly quiet. Unlike the violently luminous black holes in distant galaxies such as the quasar TON 618, whose black hole has a mass of nearly 66 billion suns, Sagittarius A-star emits relatively little radiation. It is currently in a low-activity state, swallowing only small amounts of gas and dust, but occasionally it awakens. Astronomers using NASA's Chandra X-ray Observatory have observed flares erupting from the region, each lasting just a few hours. These flares increase the black hole's brightness in X-rays and infrared by factors of up to 100. They are thought to occur when clumps of gas, or perhaps small asteroids, venture too close and are torn apart by tidal forces before vanishing into the event horizon. The region surrounding Sagittarius A-star is one of the most extreme environments in the Milky Way. Within a few light years, stars orbit at breakneck speeds. Colliding winds from massive stars create powerful shocks, and clouds of ionized hydrogen glow faintly in radio wavelengths. The temperature of gas near the black hole can reach tens of millions of degrees, while magnetic fields twist and snap like cosmic whips. In 2019, astronomers detected a cloud called G2, once believed to be a gas cloud, passing perilously close to Sagittarius A-star. Instead of being shredded completely, it survived the encounter, suggesting it might actually conceal a star at its center, wrapped in a shroud of dust. The central black hole influences the dynamics of the Milky Way's core. Within a few hundred light years, The central molecular zone contains about 60 million solar masses of gas. Sagittarius A-star's gravitational presence anchors this dense region, preventing dispersion. Its effects also indirectly influence star formation rates. In 2020, the E-Rosetta X-ray telescope detected large bubbles of hot gas extending about 45,000 light-years above and below the galaxy's center. These bubbles are thought to be the result of an eruption that took place roughly 4 million years ago, which may have been a brief flare of Sagittarius A-star. The black hole offers astronomers a natural environment for testing the laws of physics. Its extreme gravity bends space and time, providing a real-world setting for testing Einstein's general theory of relativity. During S2's closest approach in 2018, researchers from the Gravity Collaboration, using the Very Large Telescope Interferometer in Chile, measured a redshift in the star's light, confirming time dilation near the black hole, as predicted by Einstein. The galactic center provides a unique testing ground that cannot be replicated in laboratories on Earth. To study this region in finer detail, scientists have built a global telescope the size of the planet itself. The Event Horizon Telescope, EHT, a network of radio observatories spanning continents from Chile to Hawaii to the South Pole, uses a technique called very long baseline interferometry to achieve unprecedented resolution. In 2022, the EHT collaboration released the first ever image of Sagittarius A-star, showing a faint, glowing ring of superheated gas encircling a dark shadow, the outline of the event horizon. Each photon in that image had traveled for 26,700 years before reaching Earth. The result matched theoretical predictions, offering a striking visual confirmation that the monster at our galaxy's center truly is a black hole. Sagittarius A-star continues to evolve as it feeds on surrounding material. Radio telescopes detect gas drifting toward the black hole. Simulations predict that its feeding rate will fluctuate over the next few million years as gas clouds fall toward it. Future instruments, including the next generation EHT and NASA's Lynx X-ray Observatory, aim to capture real-time fluctuations in the black hole's activity, mapping how matter behaves as it spirals toward the event horizon. Observing Sagittarius A-star remains one of astronomy's most technically challenging tasks. The galactic center is an environment filled with high levels of radiation, turbulent gas, and stars that are densely packed on average, only about 0.01 light-years apart. Despite these conditions, Sagittarius A-star continues to exert measurable gravitational effects on nearby stars and gas clouds. Since its detection as a radio source in 1974 and its imaging in 2022, Sagittarius A-star has become one of the most thoroughly studied black holes. Data from telescopes across multiple wavelengths, radio, infrared, and X-ray, provide detailed information on its mass, rotation, and surrounding environment. What is a supermassive black hole? In the dark reaches of the cosmos, supermassive black holes reign as the universe's most dominant forces of gravity. Massive entities weighing millions to billions of times more than the Sunday. They occupy the centers of galaxies like cosmic monarchs, bending space-time around them, influencing the motion of stars and shaping the galactic environment. From TON 618 to the Sagittarius A-star in the Milky Way, these immense objects stand as the unseen engines behind the structure and stability of the galaxies they inhabit. Supermassive black holes differ from stellar black holes, which form from the collapse of massive stars because their masses are far greater. Their early appearance in the universe remains an open question in astrophysics. Quasars, luminous galactic nuclei, powered by accreting supermassive black holes, have been observed less than 1 billion years after the Big Bang. For instance, the quasar J 1342 plus 0928, discovered in 2017, contains a black hole 800 million times the mass of the Sun and existed about 690 million years after the universe's formation. These observations indicate that supermassive black holes formed and grew rapidly in the early universe. One possibility is that they were born from direct collapse, enormous primordial gas clouds collapsing under their own gravity to form black holes with masses between 10,000 and 100,000 suns. Another theory proposes that they grew from smaller seed black holes left behind by the universe's first generation of stars, known as population 3 stars. These ancient stars, formed about 13.5 billion years ago, were composed almost entirely of hydrogen and helium and could reach several hundred solar masses. When they collapsed, they left behind black holes that merged and accreted material over billions of years, growing into the supermassive black holes that now inhabit the centers of galaxies. At the center of every black hole is the event horizon, a boundary beyond which the escape velocity exceeds the speed of light. Within this boundary lies a singularity, where matter is compressed to extremely high density and gravitational effects dominate. For Sagittarius A-star, the event horizon's diameter is about 44 million kilometers, approximately the distance between the Sun and Mercury. The event horizon of the black hole in the M87 galaxy spans about 38 billion kilometers, comparable in size to the solar system. Surrounding the event horizon is an accretion disk, a chaotic vortex of gas and dust spiraling inward at extraordinary speeds. The material in this disk is heated by friction to temperatures reaching tens of millions of degrees, emitting intense radiation across the electromagnetic spectrum. Some of the most luminous quasars, such as 3C 273 inches, the constellation Virgo, emit light equivalent to 1 trillion suns, even from distances over 2 billion light-years away. The energy output from such accretion disks can outshine the combined light of every star in the host galaxy. When a supermassive black hole feeds, it can produce jets of charged particles that shoot out from its poles at nearly the speed of light. These relativistic jets can extend for hundreds of thousands, sometimes even millions, of light years. The jets of the radio galaxy Cygnus A, for instance, span about 300,000 light years. The black hole in M87, famously imaged by the Event Horizon Telescope in 2019, produces a jet stretching roughly 5,000 light-years, powerful enough to inject energy into its entire galactic environment. These cosmic jets influence not only the host galaxy, but also the surrounding intergalactic medium, heating gas and regulating star formation over immense regions of space. Astronomers have discovered a correlation between the mass of a supermassive black hole and the velocity dispersion of stars in the surrounding galactic bulge, known as the M-sigma relation. Identified by Carl Gebhardt and Laura Ferraris in 2000, this relationship shows that more massive black holes are found in galaxies where stars move faster within the bulge. In the Milky Way, Sagittarius A-star's 4.3 million solar masses align with the approximately 90 billion solar masses of stars in the galactic bulge, consistent with the trend observed across many galaxies. Supermassive black holes are also engines of feedback cosmic regulators that can either ignite or extinguish star formation. When a black hole consumes matter rapidly, its intense radiation and jets can blast surrounding gas away from the galactic center. This prevents new stars from forming and can even strip entire galaxies of their gas content. Observations by NASA's Chandra X-ray Observatory and the Atacama Large Millimeter, Submillimeter array ALMA, have shown that such feedback can drive outflows containing billions of solar masses of material, halting star formation for tens of millions of years. Conversely, when the outflows compress nearby gas clouds instead of dispersing them, they can trigger bursts of new star formation, a delicate balance between destruction and creation. The diversity of these giants across the universe is staggering. The central black hole of the Andromeda Galaxy, known as M31 star times, has a mass of roughly 140 million suns, while the one in NGC 4,889 inches, the Coma cluster, reaches an estimated 21 billion solar masses. Holmberg 15. A hosts one of the most massive black holes ever measured, about 40 billion solar masses, occupying a sphere of influence more than 2,000 light-years wide. Each of these titanic structures profoundly alters its host galaxy's dynamics, dictating how gas moves, how stars form, and how matter is distributed. Supermassive black holes also collide. When galaxies merge, a process that has shaped much of the universe's structure, their central black holes spiral toward one another, emitting gravitational waves as they draw closer. Once they merge, the result is a single, more massive black hole, often recoiling at speeds of thousands of kilometers per second. In 2023, scientists using pulsar timing arrays announced evidence of a background hum of gravitational waves, thought to originate from billions of merging supermassive black holes throughout cosmic history. Each collision releases an enormous amount of energy, briefly outshining all the stars in the universe combined. Supermassive black holes interact with their surroundings on every scale, from the collapse of molecular clouds to the shaping of entire galactic clusters. Around the Milky Way's core, observations by instruments such as the Gravity Interferometer and NASA's Chandra and New Star telescopes continue to reveal the behavior of matter in Sagittarius A-star vicinity. Temperatures in the accretion zone can exceed 10 million Kelvin, while magnetic fields twist and snap as gas is drawn inward. On rare occasions, flares brighten the region by factors of 100, providing fleeting glimpses of how gravity, magnetism, and light converge at the universe's most extreme frontier. The discovery of Sagittarius A-star, the story of how astronomers uncovered Sagittarius A-star, reads like a scientific detective tale spanning nearly a century. It began long before anyone had the tools or theories to grasp what was hidden behind the dense curtain of interstellar dust in the constellation Sagittarius. For decades, the galactic center was a region of speculation. Astronomers knew it existed, yet optical telescopes were blind to it. The turning point came when scientists began to listen to the universe rather than look at it, opening their instruments to radio waves that could pierce through the cosmic haze. In 1933, Carl Jansky, an engineer at Bell Telephone Laboratories, detected a repeating radio signal while studying sources of interference in transatlantic communication. The signal repeated every 23 hours and 56 minutes, the duration of a sidereal day, indicating an extraterrestrial origin. Jansky traced the signal to the direction of the Milky Way's center. His work marked the beginning of radio astronomy and provided the first evidence of radio emissions from the galactic center. After World War II, radar-based radio technology was adapted for astronomical research. By the 1,950 seconds, astronomers including John Bolton, Gordon Stanley, and Bruce Slee mapped numerous radio sources from observatories in Australia. They identified hundreds of emitters ranging from galaxies to supernova remnants and noted a particularly bright region near the Milky Way's center, designated Sagittarius A. The true nature of this radio source remained unclear until subsequent technological advancements allowed higher resolution observations. During the 1960 seconds, improvements in radio astronomy enabled the resolution of Sagittarius A into distinct components. Observations at the Owens Valley Radio Observatory and the Green Bank Interferometer revealed a compact, energetic source at the galactic center. In 1974, Bruce Ballack and Robert Brown used interferometry to connect multiple radio antennas, greatly enhancing angular resolution. Their observations identified an extremely compact radio source, smaller than Earth's orbit around the Sun, but highly luminous. Brown designated it Sagittarius A-star, with the asterisk denoting its unusual properties. Still, even this discovery raised questions. What kind of object could produce such intense energy from such a small volume of space? At first, scientists proposed exotic ideas: a cluster of neutron stars, a dense group of massive stellar remnants, or even a new type of unknown astrophysical body. But all these explanations faltered when calculations showed that the region could not remain stable if it contained ordinary matter. It would collapse within a few thousand years. The data hinted at something far denser and far more powerful. The next crucial leap came not from radio waves, but from infrared light. The galactic center is invisible to optical telescopes because of the thick interstellar dust blocking visible wavelengths. But infrared light can penetrate that veil. In the 1980 seconds, teams at the Calar Alto Observatory in Spain and later at the United Kingdom Infrared Telescope in Hawaii began detecting faint infrared emissions from stars near the galactic center. By the mid-1990 seconds, two teams, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, and another by Andrea Ghez at UCLA, began long-term monitoring of these stars with increasingly powerful infrared detectors. Over several years, astronomers tracked dozens of stars orbiting an unseen point near the galactic center with velocities of several thousand kilometers per second. One star, S2, completed a 16-year orbit, approaching within 17 light hours, about 18 billion kilometers, of the central object. The gravitational force required to maintain this orbit indicated a mass of approximately 4.3 million suns confined within a region no larger than the solar system, consistent with a supermassive black hole. Technological developments enabled these discoveries. Very long baseline interferometry (VLBI), refined during the 1970 seconds and 1980 seconds, linked radio telescopes across continents, from California to the Netherlands to South Africa, achieving milliarc-second resolution to locate Sagittarius A-star. In the 1990 seconds, adaptive optics improved ground-based infrared observations by compensating for atmospheric distortion in real time. This method, used at observatories such as Keck in Hawaii and the Very Large Telescope, VLT in Chile, produced images sharp enough to track individual stellar orbits around the galactic center. The data these instruments collected formed one of the strongest cases in modern astrophysics. By analyzing the Doppler shifts in starlight, minute changes in wavelength as stars moved toward or away from Earth, astronomers measured their speeds with unprecedented accuracy. In S2's case, the maximum velocity reached about 7,650 kilometers per second, roughly 2.5% of the speed of light. These extreme motions matched predictions for stars orbiting a compact mass governed by Einstein's general theory of relativity. Throughout the late 1990 seconds and early 2000s, the evidence accumulated relentlessly. Observations of other stars, such as S38 and S55 revealed similar elliptical orbits converging on the same invisible focus. High-resolution radio imaging from the Very Large Array in New Mexico confirmed that Sagittarius A-star was not moving relative to the galaxy's core, ruling out the possibility that it was a chance alignment of smaller sources. When astronomers compared data across wavelengths from radio to X-rays, they discovered bursts of emission, or flares, consistent with gas and dust being drawn toward an event horizon. The precision of these measurements opened new windows into extreme physics. During S2's 2018 pericenter passage, when it swept closest to the black hole, the gravity interferometer at the VLT recorded a gravitational redshift exactly as Einstein's theory predicted. Light stretched to longer wavelengths by the intense gravity near the event horizon. Later, in 2021, astronomers detected polarization in the near-infrared light from flares, offering insights into the black hole's magnetic field structure. Each of these breakthroughs depended on the decades-long foundation laid by radio pioneers like Jansky, Bolton, and Brown. Although Sagittarius A-star was identified decades earlier, confirmation of its nature required further study. Some models proposed alternatives such as dense clusters of stellar remnants or exotic particle concentrations. However, simulations indicated that such configurations would be unstable over timescales shorter than 10,000 years, while observations show Sagittarius A-star has remained stable for millions of years. By 2008, multi-wavelength data and dynamical modeling had excluded all other possibilities, confirming that Sagittarius A-star is a supermassive black hole. The scientific journey to that conclusion involved a constellation of institutions and instruments across the world. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Submillimeter Array on Mauna Kea, and the Very Long Baseline Array across North America all contributed data. Radio images of Sagittarius A-star grew sharper year by year, culminating decades later in the 2022 Event Horizon Telescope image that revealed a glowing ring of emission encircling its dark core. Each technological generation built on the last, tracing a continuous thread from Jansky's crude antenna in New Jersey to a planet-sized observatory arrayed across continents. The confirmation of Sagittarius A-star resulted from cumulative progress over many decades, involving extensive observations and technological advancement. From the first radio detection in 1933 to detailed measurements in the 21st century, astronomers have mapped the object's properties with increasing precision, providing key data on the structure of the Milky Way and on gravitational physics near supermassive black holes. Orbiting stars, clues to the invisible giant. At the very core of the Milky Way, where visible light cannot penetrate the thick clouds of gas and dust, a hidden drama unfolds, one of speed, gravity, and time itself. The stars that circle closest to Sagittarius A-star are not ordinary celestial bodies. They are survivors and witnesses, racing through warped space at unimaginable velocities around an invisible gravitational colossus. Each of these stars, locked in the black hole's relentless grip, carries within its orbit the evidence of a force powerful enough to bend light and test the boundaries of physics. The discovery of these orbiting stars, now known as the star cluster, began in the early 1992 when adaptive optics and infrared imaging revolutionized astronomy. By peering through wavelengths capable of penetrating the galactic dust, astronomers uncovered a tightly packed swarm of stars surrounding Sagittarius A-star. This region, only about 1 light-year across, is among the most crowded in the entire Milky Way. Within that space, barely 10 trillion kilometers across, hundreds of stars move in complex, intersecting paths, their trajectories controlled by an unseen gravitational anchor. These stars, labeled with designations such as S1, S2, S8, and S55, became the central evidence for the existence of the supermassive black hole at the galaxy's heart. Each orbit tells a story of cosmic violence and precision. The most well-known, S2, traces a highly elliptical path that brings it perilously close to the black hole once every 16 years. When it reached its pericenter in May 2018, S2 passed within just 17 light hours of Sagittarius A-star, roughly 3 times the distance between the Sun and Pluto, while traveling at nearly 7,650 kilometers per second. At those speeds, a journey from Earth to the Moon would take less than a minute. Observations from the European Southern Observatory's Very Large Telescope, VLT, and the Keck Observatory in Hawaii allowed astronomers to follow S2's motion frame by frame, measuring tiny displacements in its position equivalent to the width of a coin seen from thousands of kilometers away. These measurements allowed astronomers to test predictions of Einstein's general relativity. As S2 approached its pericenter, the light emitted from the star experienced gravitational redshift due to the black hole's gravity. In 2018, the Gravity Collaboration, combining data from multiple telescopes in Chile, measured this redshift, providing one of the most precise confirmations of relativity outside the solar system. S2 is not alone. Other stars, such as S38, S55, and S62, orbit even closer to Sagittarius A-star. S62, detected in 2020, appears to complete a full orbit in just over 9.9 years, making it the fastest known star in the galaxy. At its closest approach, it comes within about 16 billion kilometers of the black hole, reaching speeds estimated at 20,000 kilometers per second, nearly 7% of the speed of light. These stars are subjected to tidal forces strong enough to stretch and compress them, and their motions reveal subtle precessions, tiny shifts in their orbital paths caused by the curvature of space-time itself. Such observations allow astronomers to map the warped geometry around the black hole with unprecedented detail. Beyond testing gravity, the star cluster provides vital information about the environment of the galactic center. Many of these stars are surprisingly young, less than 10 million years old, despite residing in a region where tidal forces should prevent star formation. Astronomers refer to this puzzle as the paradox of youth. One explanation suggests that these stars formed farther out in the galaxy and later migrated inward through gravitational interactions with dense gas clouds or star clusters. Another theory proposes that massive disks of gas near Sagittarius A-star could have fragmented under their own gravity, forming new stars even in such an extreme environment. The existence of young, massive O-type and B-type stars in the cluster provides crucial insight into how matter behaves and reorganizes itself in proximity to supermassive black holes. The orbits of these stars also help define the precise gravitational reach of Sagittarius A-star. Within a radius of just 1 parsec, about 3.26 light-years, the black hole's mass dominates the galactic potential, outweighing all the stars, gas, and dust combined. Detailed modeling of their trajectories shows that 90% of the gravitational influence within this region comes directly from Sagittarius A-star, with only a small fraction contributed by other matter. This information allows astronomers to refine not just the mass of the black hole, but also its motion relative to the rest of the Milky Way. Measurements indicate that Sagittarius A-star itself is almost motionless, drifting less than 1 kilometer per second an anchor point for the entire galaxy's gravitational framework. Tracking these stars is an ongoing scientific marathon. The Keck Observatory, with its 10-meter twin telescopes, and the VLT's 4 8.2-meter units, have been continuously monitoring the galactic center for over 25 years. Adaptive optics systems use laser-guide stars to counteract atmospheric turbulence, providing image resolutions that rival those from space-based telescopes. Each observation adds another point on the star's orbital maps, gradually revealing minute deviations from purely Keplerian motion deviations that could hint at the influence of unseen forces. Scientists are particularly interested in potential perturbations caused by dark matter clumps, stellar remnants, or even intermediate mass black holes that might orbit within a few thousand astronomical units of Sagittarius A-star. In addition to tracking stellar motion, astronomers use spectroscopic data to understand the chemical and physical nature of the stars. Many of them are classified as B-type main sequence stars, with surface temperatures exceeding 20,000 Kelvin and luminosities tens of thousands of times greater than the Sun's. Some show signs of rapid rotation, spinning on their axes in just a few hours. Their energetic winds inject gas into the surrounding region, providing occasional fuel for the black hole's faint flares. These interactions between stars and the central black hole form a delicate feedback system. The stars feed Sagittarius A-star intermittently, while its gravity sculpts their orbits and influences the conditions for future star formation. The dynamics of the star cluster also help astronomers explore the distribution of stellar remnants, white dwarfs, neutron stars, and small black holes lurking near Sagittarius A-star. Theoretical models suggest that as the Milky Way evolved, massive stars sank toward the center through a process called mass segregation, leaving behind a dense population of remnants that could number in the tens of thousands within a few light years of the black hole. These objects, though mostly invisible, subtly perturb the orbits of the visible stars. Detecting these small deviations is one of the long-term goals of ongoing research, as it could unveil the hidden population of compact objects surrounding Sagittarius A-star. The data gathered since the 1,990 seconds now spans several complete orbits of S2 and partial orbits of dozens of other stars. From this long baseline, scientists can reconstruct the gravitational influence of Sagittarius A-star over time. Predictions suggest that by the 2030 seconds, new generations of telescopes, like the extremely large telescope ELT in Chile, with a 39-meter mirror, will be able to resolve stars orbiting even closer than S62. These orbiting stars act as test particles, tracing paths influenced by the curvature of spacetime near Sagittarius A-star. Their motions and Doppler shifts provide measurements of the black hole's mass and stability, as well as the behavior of matter and light in an environment with extremely strong gravity. Sagittarius A, the galactic powerhouse. Unlike ordinary stars or stellar mass black holes, whose gravity affects only their immediate surroundings, Sagittarius A-star shapes the motion of stars, gas clouds, and even the structure of the galactic bulge across several light years. Understanding its gravitational dominance is key to explaining how the Milky Way maintains its structure and why stars near the center move at extraordinary velocities. Gravity, first formalized by Isaac Newton in the 17th century, as the mutual attraction between masses reaches extreme levels near Sagittarius A-star. The black hole creates gravitational forces far beyond what Newtonian mechanics alone can describe. To accurately interpret the motions of nearby stars, astronomers turn to Albert Einstein's general theory of relativity, in which mass curves space-time, guiding the paths of both matter and light. Near Sagittarius A-star, space-time is warped so dramatically that stars trace highly elliptical orbits, and light bends noticeably as it passes near the event horizon. The star cluster, located within a fraction of a light-year from the black hole, showcases these extreme gravitational effects. Stars in this cluster reach velocities exceeding 7,000 to 500 kilometers per second, completing orbits in just over a decade. One particularly well-studied star, S2, swings as close as 120 astronomical units AU, roughly 3 times the distance from the Sun to Pluto to the black hole at its pericenter. There, S2 experiences gravitational forces millions of times stronger than those on Earth's surface. Another star, S62, moves even faster, with an orbital period of just 9.9 years and velocities exceeding 10,000 kilometers per second at closest approach, making it one of the fastest known stars orbiting a supermassive black hole. Tracking these stars over decades has allowed scientists to confirm the precise mass of Sagittarius A-star and test predictions of general relativity in a high-gravity environment. Gravity also governs the behavior of gas and dust near the galactic center. Molecular clouds, some containing hundreds of thousands of solar masses, spiral inward under the black hole's pull. Tidal forces stretch and compress these clouds, simultaneously triggering star formation in some regions while inhibiting it in others. For instance, the Brick Cloud, officially catalogued as G0 253 plus 0.016, contains roughly 50,000 solar masses and remains mostly stable despite the extreme gravitational forces around it. Meanwhile, other clouds, like G2, are heavily distorted as they approach the black hole. In 2014, G2 passed within 36 light-hours of Sagittarius A-star, about 260 AU, experiencing tidal stretching and heating that produced bright infrared emissions. Such interactions provide astronomers with natural laboratories to study gravitational dynamics and the extreme physics of matter under intense tidal forces. On a larger scale, Sagittarius A-star contributes to the stability of the galactic bulge, a dense, spheroidal region of stars surrounding the Milky Way's core. Stars within the bulge follow orbits shaped by both the black hole and the surrounding stellar mass. Measurements of velocity dispersion, which quantify how randomly stars move, correlate closely with the mass of the central black hole, a relationship known as the M-sigma relation. Observations indicate that the central velocity dispersion in the Milky Way bulge is approximately 100-120 kilometers per second, matching theoretical predictions based on Sagittarius A-star's mass. This correlation, observed across hundreds of galaxies, suggests that supermassive black holes are not merely passive residents, but active agents in galactic evolution. Extreme gravitational effects near Sagittarius A-star are also vividly apparent in tidal interactions. Occasionally, stars or gas clouds pass within the tidal radius, where differential gravitational forces can tear them apart, a phenomenon often called spaghettification. In addition to G2, another example is the star S55, which approaches within 150 AU of the black hole, where gravitational forces are strong enough to measurably distort its orbit. These encounters provide direct, observational evidence of gravity at its most extreme, offering insights into the limits of stellar survival near a supermassive black hole. The black hole's gravity affects light passing nearby. Photons experience gravitational redshift, observed during S2's 2018 close approach. The measured redshift matched predictions from general relativity to within 0.2%. Gravitational lensing can bend light from stars behind the black hole, producing multiple or distorted images, which can help map mass distribution in the central parsec and detect possible intermediate mass black holes or dark matter clumps. Observations of stellar motions near galactic centers indicate that many other galaxies harbor supermassive black holes, ranging from millions to tens of billions of solar masses, such as M87 which contains 5 billion solar masses. Their gravitational influence affects star formation rates, gas dynamics, and the distribution of dark matter within galactic cores. Studying Sagittarius A-star provides observational data for understanding these processes in other galaxies. Technological advancements have been crucial for these discoveries. Adaptive optics, interferometry, and infrared telescopes allow astronomers to observe individual stars near the black hole despite obscuring dust and gas. Instruments such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii have tracked stellar orbits for over 2 decades, providing the most compelling evidence for Sagittarius A-star's immense gravity. The Gravity Instrument, an interferometric system at VLT, has measured stellar positions with micro-arcsecond precision, enabling studies of relativistic effects in real time. Future instruments, including the extremely large telescope ELT, are expected to push these measurements further, detecting fainter stars and probing even closer to the event horizon. Sagittarius A-star exerts strong gravitational influence on stellar orbits, the flow of gas and dust, the galactic bulge, and the paths of light. Observations of these phenomena confirm the presence of a supermassive black hole, allow tests of general relativity, and provide data on star formation under extreme gravitational conditions. X-rays and radio waves. Seeing the invisible. Sagittarius A-star remains invisible to the naked eye, hidden behind thick clouds of interstellar dust and gas at the Milky Way's center. Yet its presence is betrayed by the extraordinary radiation it emits across the electromagnetic spectrum. Unlike ordinary stars, which shine in visible light, the supermassive black hole communicates through X-rays, radio waves, infrared, and gamma rays, each wavelength revealing unique aspects of the environment surrounding this cosmic giant. Observing these invisible signals allows scientists to map the flow of matter, understand energy release mechanisms, and study the high-energy physics that governs the galaxy's core. The story of unveiling Sagittarius A-star began in the 1970 seconds with radio astronomy. A compact radio source was detected at the galactic center using interferometry, a technique that combines signals from multiple radio dishes to achieve high resolution. This source, eventually named Sagittarius A-star, spans less than 1 light year, yet emits prodigious amounts of energy. Radio waves are particularly effective for studying the black hole because they penetrate the obscuring dust that blocks visible light. Modern arrays such as the Very Large Array VLA in New Mexico and the Atacama Large Millimeter, Submillimeter Array, ALMA in Chile, allow astronomers to monitor fluctuations in brightness, revealing dynamic behavior over timescales from minutes to years. X-ray observations provide a complementary perspective, tracing material heated to millions of degrees as it spirals toward the event horizon. In 2002, NASA's Chandra X-ray Observatory captured detailed images of the galactic center, revealing flares from Sagittarius A-star that brightened by factors of up to 100 within a few hours. These sudden eruptions are thought to result from magnetic reconnection events, in which tangled magnetic fields snap and release tremendous energy, or from the accretion of dense gas clumps. By measuring the temperature, density, and composition of the X-ray emitting gas, often exceeding 10 million Kelvin. Astronomers can model the structure of the accretion flow and estimate the efficiency of energy conversion near the black hole. Infrared observations are vital for tracking stars orbiting close to Sagittarius A-star. Infrared light penetrates the dust that obscures visible wavelengths, allowing precise measurements of stellar positions and velocities. Observatories have monitored stars like S2, S62, and S55 for decades. These observations confirm the presence of a 4.3 million solar mass black hole and provide critical tests of general relativity. Infrared studies also reveal cooler gas clouds heated by nearby stars or shock waves, mapping structures within a few parsecs of the black hole and showing how Sagittarius A-star influences its immediate environment. At the highest energies, gamma-ray observations trace particles accelerated to near-light speeds. While the Milky Way's central black hole is currently quiescent compared to active galactic nuclei in other galaxies, gamma-ray studies using telescopes like Fermi-Lat suggest that Sagittarius A-star has experienced periods of intense activity in the past. Such outbursts may have injected vast amounts of energy into the surrounding interstellar medium, shaping gas dynamics over distances of thousands of light-years. These observations indicate that even a relatively quiet black hole can leave long-lasting imprints on its galaxy. Multi-wavelength studies are crucial for connecting these different phenomena. Coordinated campaigns using Chandra X-rays, ALMA millimeter radio, and infrared observatories have captured flare events simultaneously across multiple bands. Time delays between X-ray and radio peaks, often on the order of 20-30 minutes, reveal how energy propagates from the innermost regions near the black hole outward through surrounding gas. These observations allow scientists to constrain the size of emitting regions, estimate magnetic field strengths, frequently reaching tens of Gauss, and refine models of accretion and particle acceleration near the event horizon. Radio astronomy has evolved dramatically in recent years. The Event Horizon Telescope, a global network of radio observatories, can resolve structures near Sagittarius A-star's event horizon with unprecedented precision. Observations at 1.3 millimeter wavelengths detect fluctuations in brightness and shape caused by orbiting hotspots or turbulent magnetic fields. In 2022, the EHT captured the first detailed image of the region surrounding Sagittarius A-star, revealing an asymmetric ring of emission approximately 52 micro-arcseconds across, equivalent to the size of a grapefruit on the Moon as seen from Earth. These radio signals provide direct evidence of matter orbiting at relativistic speeds and offer an unparalleled view of extreme gravity in action. High-energy radiation from the galactic center also interacts with gravity in striking ways. Gravitational redshift affects X-rays emitted near the event horizon, reducing their energy as photons escape the black hole's deep gravitational well. Additionally, gravitational lensing can bend the paths of radio or infrared light, creating distorted or multiple images of background stars or gas clouds. By studying these effects, astronomers can test predictions of general relativity under conditions far beyond what is achievable on Earth, effectively turning Sagittarius A-star into a natural laboratory for fundamental physics. Unexpected structures have been detected through non-visible light. Radio observations reveal a faint, jet-like extension protruding from Sagittarius A-star, weaker than the jets seen in galaxies such as M87. X-ray surveys detect diffuse hot gas in the central parsec, with temperatures ranging from 5-10 million Kelvin, indicating heating and turbulence near the black hole. Gamma-ray studies suggest the presence of high-energy cosmic rays, possibly accelerated in shocks near the black hole or from interactions with molecular clouds. These observations provide evidence of Sagittarius A-star's influence on its surrounding environment. Technological innovations continue to enhance observational capabilities. Adaptive optics in infrared telescopes correct for atmospheric distortion, producing diffraction-limited images of stars just milliarc-seconds apart. Advances in radio interferometry achieve resolutions of tens of microarc-seconds, effectively creating a telescope as large as the Earth itself. Space-based X-ray observatories bypass atmospheric absorption entirely, capturing radiation that would otherwise be blocked. Combined, these techniques provide detailed, multi-wavelength data of the galactic center, enabling study of phenomena that were previously inferred only theoretically. The role of Sagittarius A in galactic formation. Supermassive black holes, like Sagittarius A-star, exert influence far beyond their immediate vicinity, sculpting stellar populations, regulating gas dynamics, and shaping the distribution of dark matter. The interplay between the black hole, surrounding stars, interstellar gas, and cosmic dust drives, processes that determine the structure of the bulge, disk, and spiral arms. Understanding this dynamic relationship provides crucial insights into galaxy formation across the universe. Galaxies emerge from the collapse of vast clouds of gas embedded within dark matter halos. During the early stages, star formation begins as dense clumps ignite nuclear fusion, releasing energy that heats and disperses surrounding gas. The presence of a central mass concentration like Sagittarius A-star stabilizes the inner galaxy, preventing chaotic dispersal of stars and gas. Observations suggest that the Milky Way's bulge, a spheroidal cluster of roughly 10 billion stars within a radius of 21 kiloparsec, owes its cohesion in part to the gravitational influence of the black hole, whose core anchors stellar orbits in coherent patterns. Sagittarius A-star influences star formation through energetic feedback. Material falling into the black hole is not fully absorbed. Some is expelled as high-energy radiation, stellar winds, or weak jets. These outflows heat surrounding gas, which can either suppress or trigger new star formation. Dense molecular clouds within the central 5 parsecs experience turbulence from past flares, delaying gravitational collapse, while shock waves from energetic events compress more distant clouds, stimulating star formation. Infrared surveys of the central molecular zone using instruments like the ALMA array reveal filaments of gas moving at 5,200 kilometers per second. Observed star formation rates near the galactic center range from roughly 0.1–0.5 solar masses per year, affecting the evolution of the bulge over billions of years. Detailed measurements of stellar orbits, most notably stars in the star cluster such as S2, which completes an orbit every 16 years, show that stars within the inner 5 light-years respond primarily to the black hole's gravity. These orbits help maintain the structure of the galactic core. Simulations indicate that without this central mass, stars in the inner galaxy could scatter, potentially thickening the disk and destabilizing spiral structures. Gas inflows toward the black hole also affect galactic evolution. Over tens of millions of years, streams of molecular hydrogen and carbon monoxide spiral inward under gravitational influence. These inflows feed both star formation and black hole accretion in cycles. High accretion periods produce energetic outbursts that expel gas, while quieter intervals allow cooling and accumulation. Observations of the central 100 parsecs revealed dense clumps moving at 100 to 300 kilometers per second, tracing spiral-like filaments feeding Sagittarius A-star. These processes affect the distribution and composition of gas and stars in the central region. Chemical enrichment near the galactic center is influenced by black hole activity. Massive stars form, evolve, and explode as supernovae, releasing elements such as carbon, oxygen, and iron into surrounding gas. Outflows and shocks from black hole activity mix this material through the bulge, creating a gradient in metallicity. Stars near the center are richer in heavy elements compared with those in the outer disk. Spectroscopic studies from the Keck Observatory and VLT confirm this gradient, showing central metallicities around Phi-H is approximately equal to plus 0.3, while outer disk stars average closer to Phi-H is approximately equal to negative 0.1. This chemical redistribution contributes to the composition of subsequent generations of stars. Sagittarius A-star follows a correlation observed in many galaxies between black hole mass and bulge mass, known as the M-sigma relation. The Milky Way's central black hole and stellar bulge evolved together. Accretion onto Sagittarius A-star influenced star formation rates, gas inflows, and the galaxy's dynamical structure, while the bulge's gravitational potential affected how efficiently the black hole captured in falling material. Comparative studies of other galaxies reinforce the importance of central black holes. In active galaxies like M87 or NGC 1275, jets extend thousands of light years, reshaping gas clouds and sometimes quenching star formation. While Sagittarius A-star is relatively quiescent today, indirect evidence suggests past active phases. Observations of the Fermi bubbles, gigantic gamma-ray emitting lobes extending over 25,000 light-years above and below the galactic plane, point to energetic events roughly 6 million years ago, likely triggered by enhanced accretion onto the black hole. These bubbles demonstrate that even a currently quiet black hole can profoundly influence galaxy-scale structure over time. Central black holes influence star formation and gas dynamics during galaxy interactions and mergers. In galaxy clusters, supermassive black holes help prevent runaway cooling of hot gas in central regions, maintaining structural stability over billions of years. Studying Sagittarius A-star provides observational data on these processes at the scale of a single galaxy. Technological advances have enabled detailed mapping of these relationships. The Very Large Array traces radio emission from molecular clouds. ALMA resolves fine-scale gas filaments, and the Chandra X-ray Observatory detects past outbursts and hot gas. Combined datasets reveal complex flows, stellar motions, and evidence of historical energetic events. Infrared surveys, adaptive optics, and long-term stellar monitoring refine understanding of how Sagittarius A-star interacts with the surrounding bulge and disk. Sagittarius A-star stabilizes stellar orbits, influences gas inflows, drives chemical enrichment, and affects star formation, impacting the structure of the Milky Way over billions of years. Its influence extends from the inner 0.1 parsecs to the outer bulge, linking gravitational dynamics with energetic feedback and chemical evolution. Observations of Sagittarius A-star provide data on mechanisms that govern galaxy formation, accretion disks, and cosmic fireworks. At the very heart of Sagittarius A-star, matter rarely falls directly into oblivion. Instead, it forms a brilliant and turbulent structure known as an accretion disk, a swirling ring of gas, dust, and stellar debris, spiraling ever closer to the black hole's event horizon. These disks act as cosmic engines, converting gravitational energy into heat and radiation. The result is one of nature's most spectacular phenomena, a dynamic, luminous display of energy that transforms invisible gravity into a show of cosmic fireworks. Accretion disks form when material from nearby stars, interstellar gas, or even tidally disrupted planets becomes trapped by the black hole's gravity. As this material orbits closer, it heats to millions of degrees through friction and compression, releasing radiation across the electromagnetic spectrum, from radio waves to high-energy X-rays. In a supermassive black hole like Sagittarius A-star, this process can release as much as 10% of the infalling matter's rest mass as energy, a conversion rate far exceeding that of nuclear fusion in stars. Unlike the quasars at the centers of distant galaxies, Sagittarius A-star is a low-luminosity active galactic nucleus, LLAGN, emitting less than 10 to the power of -9 times the Eddington luminosity, the theoretical maximum, before radiation pressure prevents further accretion. X-ray and infrared telescopes, including Chandra, XMM Newton, and the Very Large Telescope, have observed sudden flares that increase brightness at the galactic center by up to 150 times. These flares, lasting from 30 minutes to a few hours, trace activity within a few Schwarzschild radii of the event horizon. The accretion disk exhibits strong turbulence and magnetic activity. Within roughly 10-100 times the event horizon radius, hot plasma moves at relativistic speeds. Magnetic fields within this plasma can reconnect, releasing energy that may cause many of the flares observed from Sagittarius A-star. Measurements of polarized light by the Event Horizon Telescope in 2022 indicate that the accretion flow is magnetically dominated, with magnetic field lines arranged in twisted circular structures around the event horizon. As matter in the accretion disk spirals inward, it loses angular momentum through friction and magnetic turbulence. This process, described by the magnetorotational instability MRI, allows gas to drift closer to the black hole while transferring energy outward. In Sagittarius A-star, this inflow occurs at a trickle about 10 to the power of -9 solar masses per year, but even that is enough to heat surrounding gas to temperatures exceeding 10 million Kelvin. The result is faint yet measurable radiation in radio and X-ray bands. The outer regions of the disk behave differently. There, cooler gas forms dense filaments and clumps that gradually feed the inner zone. Infrared observations using ALMA and Keck Observatory have detected knots of warm hydrogen and ionized iron orbiting hundreds of astronomical units from Sagittarius A-star. These knots occasionally destabilize, sending gas inward in bursts. Each influx can trigger new flares, changing the brightness and temperature of the inner accretion flow. Accretion disks transfer energy into the surrounding environment through high-energy photons, particle winds, and outflows. Observations with the Chandra X-ray Observatory and ALMA have revealed expanding shells of ionized gas, remnants of past accretion outbursts, moving at velocities up to 1,000 kilometers per second. These outflows influence star formation near the galactic center by altering local gas temperatures and densities. The accretion disk of Sagittarius A-star exhibits variability characterized by frequent flare events. Over the past 2 decades, more than 4,000 flares have been recorded, ranging from minor fluctuations to major bursts. Statistical analyses from NASA's Chandra and ESA's XMM Newton missions indicate that these flares follow a power law distribution. Smaller flares occur more often, while larger ones are rarer and more energetic. Flares are associated with processes such as magnetic instabilities, colliding gas clumps, or infalling stellar debris. In comparison with active galaxies such as 3C 273 or TON 618, which exhibit accretion disk luminosities exceeding 10 to the power of 47 ergs per second, Sagittarius A-star emits about 10 to the power of 36 ergs per second. Studying this emission helps constrain models of low-efficiency accretion and the range of luminosities among supermassive black holes. Observations suggest that black holes can alternate between low-activity and high-activity phases. Modern observational tools are now capturing the accretion disk of Sagittarius A-star in exquisite detail. The Event Horizon Telescope, which produced the first image of the Milky Way's black hole in 2022, showed a bright, asymmetric ring of emission surrounding a dark shadow, the silhouette of the event horizon itself. The size of this ring, roughly 50 microarcseconds, perfectly matched predictions from Einstein's general relativity. Ongoing EHT observations at multiple wavelengths continue to refine our understanding of how matter swirls and radiates at the edge of a black hole. Accretion disks are not just sources of electromagnetic radiation, they may also generate gravitational waves. Asymmetries in the flow, orbiting clumps of matter, or the capture of compact objects like neutron stars could produce ripples in space-time detectable by future instruments such as the Laser Interferometer space antenna. Although current detectors cannot sense these faint waves from Sagittarius A-star, simulations suggest that their signatures might become measurable within the next 2 decades, offering an entirely new way to probe accretion dynamics. The accretion disk of Sagittarius A-star involves plasma turbulence, relativistic motion, and magnetic reconnection on small scales, while influencing gas dynamics and energy distribution in the Milky Way's central region on larger scales. Observed variability reflects the interaction of gravitational, magnetic, and kinetic processes near the event horizon, flares and magnetic fields. Sagittarius A-star is often portrayed as a dormant gravitational titan, but beneath its quiet exterior lies a restless, flickering heart. Periodically, it erupts with sudden outbursts of energy, known as flares, brief yet powerful bursts, detectable in X-ray, infrared, and radio wavelengths. These events are windows into the turbulent physics at the galaxy's core, revealing the interplay of gravity, plasma, and magnetic fields under conditions impossible to reproduce on Earth. The discovery of these flares marked a turning point in understanding Sagittarius A-star. In October 2001, NASA's Chandra X-ray Observatory recorded a sudden increase in X-ray brightness from the galactic center that lasted roughly 3 hours, during which the luminosity rose by a factor of 45. Since then, telescopes like XMM Newton, the Very Large Telescope, Keck Observatory, and Spitzer have recorded hundreds of similar outbursts. Typical flares occur several times per day, lasting from a few minutes to several hours, and increasing brightness by factors ranging from 10 to 150. The rapid variability indicates that these emissions arise from a region only a few dozen times the Schwarzschild radius, mere tens of millions of kilometers from the event horizon itself. Magnetic fields are a primary driver of these flares. The plasma that orbits Sagittarius A-star in its inner accretion flow is fully ionized and interacts strongly with magnetic forces. As it moves at relativistic speeds, differential rotation stretches and twists magnetic field lines into complex configurations. When these field lines reconnect, a process called magnetic reconnection, they release large amounts of magnetic energy. This accelerates electrons to near light speed, producing radiation in X-ray and infrared wavelengths. Magnetic reconnection near Sagittarius A-star is orders of magnitude more powerful than the same process observed in our Sun's corona. Estimates suggest magnetic field strengths near the black hole can reach 30 to 100 Gauss, compared to about 1 Gauss in the solar photosphere. A single large flare can release up to 10 to the power of 39 ergs of energy, equivalent to the Sun's total output over several days, concentrated into a few hours. Observations by XMM Newton have recorded X-ray peaks reaching 10 to the power of 35 ergs per second, confirming the enormous energy release during these transient episodes. Some flares are associated with small-scale ejections of plasma. In 2019, coordinated observations by Chandra, ALMA, and the gravity instrument at the VLT detected an infrared flare followed by delayed radio emission, indicating that a magnetized plasma structure was ejected from the inner disk before cooling and fading. The ejected material appeared to move outward at about 0.3 times the speed of light, suggesting the presence of compact, transient outflows similar to scaled-down versions of jets in active galaxies. Flares also provide direct evidence for relativistic motion near the event horizon. Observations with the VLT's gravity interferometer in 2018 captured infrared flares orbiting Sagittarius A-star at roughly 30% of the speed of light, completing a circuit every 45 minutes. These flares followed predicted general relativistic trajectories, showing light being bent and beamed by the black hole's intense gravity. The data provided one of the most precise confirmations yet of Einstein's theory in the strong field regime. The environment that produces flares is shaped by interactions between the accretion flow and nearby stars. For example, the star S2 approaches as close as 17 light hours to the black hole during its pericenter passage. When S2 sweeps through the dense gas near the galactic center, it can perturb magnetic structures and compress plasma, potentially triggering increased flare activity. This was observed during the star's close approach in 2018, when X-ray and infrared flaring rates briefly doubled, suggesting a connection between stellar winds and the black hole's magnetic field dynamics. Polarimetric studies of Sagittarius A-star have been key to understanding its magnetic geometry. Measurements of polarized infrared and radio light by the Event Horizon Telescope and submillimeter array reveal that the magnetic fields near the event horizon are both ordered and dynamic. The polarization angle varies over time, implying that magnetic loops rotate and evolve as plasma orbits the black hole. Such observations also indicate that the magnetic field is strong enough to channel material into the accretion flow while stabilizing it against destructive turbulence. The frequency and intensity of flares provide clues to the black hole's feeding rate and energy output. Statistical studies based on 2 decades of Chandra and XMM Newton data show that Sagittarius A-star produces several hundred measurable flares per year, with luminosities following a power law distribution. Smaller flares, only a few times the baseline brightness, occur daily, while major events occur a few times per month. This pattern suggests that the accretion process is episodic, driven by stochastic magnetic instabilities rather than steady inflow. These events also allow astronomers to test how magnetic energy converts into radiation. During reconnection, accelerated electrons emit synchrotron radiation as they spiral along magnetic field lines, producing polarized infrared light. When these electrons collide with photons from nearby stars or dust, they upscatter them into X-rays via inverse Compton scattering. This 2-step emission mechanism explains the simultaneous X-ray and infrared flares observed by multi-wavelength campaigns combining Chandra, VLT, and Keck. Comparisons with other galaxies, such as M87, which hosts a black hole roughly 1,500 times more massive, show that similar magnetic and accretion processes occur at different scales. M87's jet extends about 5,000 light-years, while Sagittarius A-star exhibits weaker flares corresponding to a luminosity less than 10 to the power of -8 of its Eddington limit. These comparative studies characterize the range of behaviors between low-activity and high-activity galactic nuclei. Flares from Sagittarius A-star provide observational data on magnetic field dynamics, relativistic particle acceleration, and light bending near the event horizon. These events contribute to understanding the physical conditions and processes that occur in the strong gravity environments surrounding black holes. Observations of transient flares from Sagittarius A-star indicate that the black hole exhibits dynamic, magnetic, and radiative behavior detectable in X-rays, radio, and polarized infrared light. These measurements continue to inform models of accretion, magnetic reconnection, and plasma dynamics near the event horizon. Measuring mass. How heavy is the giant? Weighing a black hole might seem impossible. After all, Sagittarius A-star emits no light, offers no surface to study, and hides behind 26,700 light-years of gas and dust. Yet, astronomers have managed to determine its mass with remarkable precision, about 4.1 million times the mass of the Sunday. This extraordinary measurement, achieved through decades of patient observation and technological ingenuity, lies at the heart of our understanding of both the black hole and our galaxy's structure. The story begins in the 1970 seconds, when radio astronomers using the Green Bank interferometer and later the Very Large Array identified an unusually compact, bright radio source in the constellation Sagittarius. They called it Sagittarius A, and within it, a denser, unresolved region, Sagittarius A-star, hinted at something massive yet invisible. Early estimates suggested a powerful gravitational source, but its true mass and nature remained uncertain until infrared astronomy matured in the late 20th century. The measurement of Sagittarius A-star's mass was achieved by tracking the orbits of stars near the galactic center. In the early 1990 seconds, two research teams, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, and another by Andrea Ghez at UCLA, used large ground-based telescopes, including the New Technology Telescope, Keck Observatory, and later the Very Large Telescope, with adaptive optics to correct atmospheric distortion. This technology enabled precise measurements of stellar positions at the galactic center with milli-arc-second accuracy, comparable to resolving a coin on the moon. Among these stars, one emerged as the key to the mystery, S2, also known as S0-2. S2's elliptical orbit around the galactic center takes 16.05 years, and at its closest approach, the star comes within just 17 light hours, about 120 astronomical units of Sagittarius A-star. During this periapsis passage, S2 reaches speeds exceeding 7,650 kilometers per second, or about 2.5% of the speed of light. By applying Kepler's laws of orbital motion, astronomers could calculate the mass enclosed within S2's orbit, confined within a radius smaller than Mercury's orbit. Further validation came from other stars. S0-102, with an orbital period of 11.5 years, follows an even tighter trajectory, providing an independent check of the gravitational field. Additional stars, such as S38, S55, and S4711 have orbits consistent with a single dominant mass at the center. Statistical modeling of these orbits ruled out the possibility of a dense cluster of dark stellar remnants, confirming that the central object is a supermassive black hole. Astronomers also turned to gas dynamics for confirmation. Using radio and infrared observations from facilities such as ALMA and the Atacama Pathfinder experiment, APEX, they mapped the velocity of ionized gas clouds orbiting within the central 1 parsec. These gases, primarily hydrogen and carbon monoxide, move at hundreds of kilometers per second, following paths that align perfectly with the gravitational potential inferred from the stellar orbits. Models of these flows independently yield a mass between 4 and 4.3 million solar masses, reinforcing the stellar data. To further refine measurements, researchers studied the nuclear star cluster surrounding Sagittarius A-star. This dense cluster, spanning about 10 light-years, contains hundreds of thousands of stars with diverse velocities. By modeling the stellar motions, astronomers derived a central mass consistent with measurements from individual stellar orbits and gas dynamics. These independent methods converge on a value of about 4.1 million solar masses, making Sagittarius A-star one of the most precisely characterized supermassive black holes. Technological advances have played a central role in this measurement. Adaptive optics stabilize infrared images distorted by Earth's atmosphere, while interferometry, combining light from multiple telescopes, provides micro-arcsecond resolution. The gravity instrument on the VLT interferometer has refined positional accuracy to about 10 micro-arcseconds, allowing detailed tests of gravitational dynamics and relativistic effects near the black hole. The measurement of Sagittarius A-star's mass contributes to studies of galactic evolution. When compared with data from other galaxies, it aligns with the M-sigma relation, which links black hole mass to the velocity dispersion of stars in a galactic bulge. In the Milky Way, the ratio between Sagittarius A-star's mass and the bulge mass to 10 to the power of 10 solar masses matches this trend, supporting models of coevolution between black holes and their host galaxies. Knowing the black hole's exact mass also refines tests of Einstein's general theory of relativity. During S2's closest approach in May 2018, astronomers observed a gravitational redshift of the stretching of the star's light as it escaped the black hole's gravitational field. Continued monitoring of S2 and other short-period stars will allow researchers to probe even subtler effects, such as Schwarzschild precession, where an orbit's ellipse gradually rotates due to space-time curvature. Sagittarius A-star is comparatively small among known supermassive black holes. The black hole in the galaxy M87, imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses, over 1,000 times greater. Others, such as TON 618, exceed 60 billion solar masses. This difference illustrates variation in black hole growth histories. Sagittarius A-star likely experienced gradual accumulation rather than large-scale mergers or high accretion rates. Accurate mass measurement also aids in predicting future phenomena. It allows astronomers to calculate when stars, gas clouds, or even hypothetical objects like dark matter clumps might pass close enough to trigger observable flares or accretion events. For example, the 2014 encounter of the gas cloud G2 with Sagittarius A-star was modeled in part using mass-derived gravitational parameters, enabling scientists to anticipate its trajectory and the resulting X-ray emission. The mass measurement of Sagittarius A-star demonstrates the precision achievable in modern observational astronomy. Decades of data have constrained the black hole's mass to within about 15% uncertainty, establishing Sagittarius A-star as one of the best characterized supermassive black holes currently known. With 4.1 million solar masses concentrated within a region smaller than the solar system, Sagittarius A-star exerts a dominant gravitational influence on nearby stars and stabilizes the Milky Way's central bulge. This measurement defines the mass distribution at the galaxy's core and provides a basis for models of galactic dynamics. Inside the event horizon, the point of no return. At the very center of the Milky Way lies the most mysterious frontier in the cosmos, the event horizon. It is not a surface or a tangible barrier, but rather a point of no return, the invisible boundary beyond which space and time are so severely curved that escape is impossible. Once matter, or light, crosses this threshold, it becomes forever severed from the rest of the universe. For astrophysicists, understanding this boundary is key to deciphering how black holes interact with their surroundings and how they shape the structure and destiny of galaxies. The event horizon emerges naturally from Einstein's general theory of relativity. Published in 1915, the theory redefined gravity as the warping of space-time by mass and energy. When enough matter is compressed into a sufficiently small region, the curvature becomes infinite, creating a region where the escape velocity exceeds the speed of light. For a non-rotating black hole, like the idealized model described by Carl Schwarzschild in 1916, this critical boundary occurs at the Schwarzschild radius, calculated by the formula R-red equals 2gm divided by c squared. For Sagittarius A-star, the Schwarzschild radius is approximately 12.7 million kilometers, roughly 17 times the radius of the Sun, or 0.085 astronomical units. This entire mass, compacted within a region smaller than Mercury's orbit, generates gravity so intense that even photons cannot escape. Yet the event horizon is not a static feature. For a rotating black hole, described by the Kerr metric, the boundary changes shape and introduces additional structures, such as the ergosphere, a region outside the horizon where space-time itself is dragged along by the black hole's spin. Astronomers suspect that Sagittarius A-star rotates at a moderate rate, perhaps between 30% and 60% of the maximum possible spin, which would slightly flatten its event horizon and influence how energy and radiation emerge from the surrounding plasma. Detecting the exact degree of rotation remains one of the primary objectives of ongoing observations. From an external reference frame, an object falling toward the horizon appears to slow indefinitely, its light increasingly redshifted due to gravitational time dilation. To the object itself, the crossing occurs rapidly, with no physical boundary at the horizon. Observations of the star S2, which passes within about 120 astronomical units of Sagittarius A-star, show redshift behavior consistent with relativistic predictions, confirming that general relativity remains valid in strong gravitational fields. The region just outside the event horizon is one of the most violent environments in the known universe. As matter spirals inward, it forms a hot, magnetized accretion flow that reaches temperatures of millions of degrees. The gas emits across the electromagnetic spectrum from radio waves to X-rays, allowing astronomers to probe the physics of space-time's edge indirectly. Instruments like NASA's Chandra X-ray Observatory, NuSTAR, and ESA's XMM Newton have detected high-energy flares and rapid brightness variations, originating mere light minutes from the horizon, revealing plasma dynamics that change on timescales of minutes to hours. These emissions help trace the flow of matter as it approaches the fatal boundary. Direct imaging of the region surrounding the event horizon became possible only recently. In 2022, the Event Horizon Telescope, a global network of radio observatories released the first image of Sagittarius A-star. Using very long baseline interferometry, VLBI, the EHT achieved angular resolution of about 20 micro-arcseconds. The resulting image showed a bright ring of emission around a dark central region corresponding to the shadow of the event horizon. The measured ring diameter of about 52 micro-arcseconds agrees with theoretical predictions for a massive black hole. The apparent darkness at the center of the image is not an actual hole, but a photon capture zone where light is gravitationally trapped before being swallowed. The bright ring represents material orbiting just outside the innermost stable circular orbit, ISCO, where gravity, magnetism, and rotation balance precariously. In Sagittarius A-star, this radius is about 1.5 times the Schwarzschild radius, depending on spin. The light from this region, bent by the extreme curvature of space-time, forms the glowing halo captured by the EHT. The event horizon also affects the surrounding galactic environment. Gravitational interactions influence the motion of nearby stars and gas clouds within several light-years of Sagittarius A-star. Over long timescales, the black hole gradually accumulates material from stellar winds, disrupted stars, and in falling gas. The current accretion rate is low, roughly equivalent to 1 lunar mass per year. But over billions of years, this steady inflow contributes to the black hole's mass and its role as the Milky Way's central gravitational anchor. The vicinity of the event horizon provides a natural environment for testing ideas that link quantum mechanics and gravity. In 1974, Stephen Hawking proposed that black holes emit weak radiation arising from quantum fluctuations near the horizon, now called Hawking radiation. For supermassive black holes such as Sagittarius A-star, this radiation is far too faint to detect directly. The predicted temperature is about 10 to the power of negative 14 kelvins. Nevertheless, the concept connects black hole thermodynamics, entropy, and information theory, and the associated information paradox remains an open question in theoretical physics. Astronomers continue to probe the horizon indirectly through time-variable emissions, polarization studies, and gravitational modeling. Observations with the gravity interferometer at the Very Large Telescope Interferometer have tracked hotspots orbiting at roughly 30% of light speed, just above the event horizon, consistent with models of magnetically driven plasma loops. Meanwhile, EHT's ongoing campaigns, augmented by new stations in Greenland and Africa, aim to capture time-resolved movies of Sagittarius A-star, showing how matter flows and dissipates near the horizon on hourly scales. The event horizon marks the region where current physical theories become incomplete. Beyond this boundary, general relativity predicts a singularity where density and space-time curvature diverge. By investigating phenomena near the horizon, researchers test the limits of existing theories and seek frameworks that unify gravity and quantum mechanics. For the Milky Way, the event horizon of Sagittarius A-star defines the gravitational boundary that governs the structure of the galactic core and the motions of nearby stars. Continued observation of this region provides data for testing gravitational models and understanding the dynamics of matter under extreme conditions. Sagittarius A versus other supermassive black holes. Sagittarius A-star, the supermassive black hole at the core of the Milky Way, serves as humanity's closest and most detailed window into one of the universe's most extraordinary phenomena. Yet, when compared to other supermassive black holes scattered throughout the cosmos, Sagittarius A-star seems modest, quiet, compact, and almost restrained in its behavior. Studying how it differs from its cosmic counterparts provides essential insight into the full spectrum of black hole evolution, from dormant galactic centers like ours to the blazing hearts of quasars, that dominated the early universe. Supermassive black holes come in an astonishing range of sizes and power outputs. Their masses stretch from a few 100,000 to tens of billions of solar masses, depending on the size, age, and type of the host galaxy. Sagittarius A-star sits on the smaller end of this scale, a featherweight compared to cosmic leviathans such as M87 star in the Virgo cluster. The black hole in M87 boasts a staggering 6.5 billion solar masses, over 1,500 times more massive than Sagittarius A-star. Even larger examples exist. TON 618, a hyperluminous quasar more than 10 billion light-years away, harbors a black hole estimated at 66 billion solar masses, one of the most massive ever identified. The range of sizes suggests that black holes grow under vastly different conditions, influenced by the availability of gas, merger history, and the density of the surrounding cosmic environment. Activity level represents another key difference. Sagittarius A-star is classified as quiescent, meaning it accretes matter at a very low rate, roughly the mass of the Moon per year. Its X-ray luminosity hovers around 10 to the power of 33 ergs per second, about 1 billion times weaker than the output of luminous quasars. In contrast, the central black hole of the quasar, 3C 273, located 2.4 billion light-years away, radiates at nearly 10 to the power of 46 ergs per second, outshining entire galaxies. These active galactic nuclei, AGN, derive their brilliance from intense accretion. Enormous disks of gas and dust spiral inward, heating to millions of degrees and unleashing energy equivalent to trillions of suns. While Sagittarius A-star dozes in relative calm, these energetic black holes rage as cosmic engines that can reshape their galaxies. Spin, too, defines much of a black hole's behavior. Rotation determines how efficiently a black hole can convert infalling matter into energy. Observations of M87 star suggest it spins at a rate near 0.9 of the maximum allowed by relativity, enabling it to launch powerful relativistic jets, extending over 5,000 light-years from the galactic core. These jets, detected in both radio and X-ray wavelengths, pierce the intergalactic medium and inject enormous energy into surrounding space. Sagittarius A-star, in contrast, shows no such large-scale jets. Its modest spin and low accretion rate keep it subdued. Current estimates, derived from modeling flare polarization and radio emission patterns, indicate Sagittarius A-star's spin lies between 0.3 and 0.6, moderate by cosmic standards. The environments of supermassive black holes vary significantly with galaxy type. Sagittarius A-star lies within the Milky Way's nuclear star cluster, surrounded by stars, molecular clouds, and remnants of past stellar generations. This region is relatively transparent at infrared and radio wavelengths, allowing direct observation of the black hole's surroundings. In contrast, the centers of active galaxies, such as NGC 1068 and Centaurus A, are obscured by dense dust and gas, where radiation pressure from luminous accretion disks drives large-scale outflows and winds that hinder direct imaging. The growth histories of these cosmic giants tell the story of the universe itself. Sagittarius A-star likely formed around 13 billion years ago, perhaps from the collapse of a massive primordial gas cloud, or through the merger of smaller seed black holes. Since then, it has grown gradually, accumulating mass from stellar debris and occasional gas infall. Other black holes, however, experienced periods of explosive growth. During the epoch known as cosmic noon, roughly 10 billion years ago, quasars like ULAS J 1000, 342 plus 0928 with a redshift of 7.5 already harbored black holes exceeding 800 million solar masses, implying rapid early formation mechanisms that remain poorly understood. These massive black holes consumed material at extraordinary rates, shaping galaxy evolution across the young cosmos. The gravitational and energetic influence of a supermassive black hole scales with its mass and activity level. Sagittarius A-star affects stellar motions within a few light years of the galactic center, including stars such as S2 and S4000, 716, which orbit at speeds up to 24,000 kilometers per second. In galaxies hosting larger black holes like M87 or NGC 4889, gravitational effects extend for thousands of light years and can influence the surrounding interstellar medium. Energy released through accretion and jets heats nearby gas, reducing star formation efficiency and regulating the growth of the host galaxy. Recent technological advances have enabled direct comparison between supermassive black holes. The Event Horizon Telescope collaboration imaged both Sagittarius A-star in 2022 and M87 star in 2019, revealing similar ring-like emission patterns that match general relativistic models. Because Sagittarius A-star is over 1,500 times less massive, the orbital timescales near its event horizon are minutes rather than days, causing rapid brightness variability. To create a stable image, EHT researchers combined thousands of short observations, demonstrating the complexity of imaging smaller, variable black holes. Comparative studies of supermassive black holes also reinforce key galactic correlations. The M-sigma relation, which links black hole mass to the velocity dispersion of stars in the galactic bulge, holds true across a wide range of galaxies. Sagittarius A-star, with a bulge stellar velocity dispersion of about 100 kilometers per second, fits perfectly within this relation, confirming that the same physical mechanisms governing galaxy black hole coevolution apply to both small and large systems. This relationship hints that black holes and galaxies evolve symbiotically, each regulating the other's growth through feedback processes that operate over cosmic timescales. Sagittarius A-star's proximity makes it invaluable for testing these broader theories. While distant quasars provide examples of high-energy extremes, Sagittarius A-star allows precise, time-resolved measurements of relativistic effects, stellar orbits, and magnetic field interactions. Instruments such as gravity at the Very Large Telescope Interferometer and Chandra's X-ray spectrometer have captured minute fluctuations in brightness and motion that reveal how matter behaves just outside the event horizon. These local insights anchor the interpretation of distant observations, bridging the gap between calm and chaotic black holes across the universe. Within the observed population of supermassive black holes, Sagittarius A-star represents a low luminosity example that offers detailed observational access. Its stable, low activity state enables precise measurement of gravitational, magnetic, and relativistic effects that are harder to isolate in more energetic systems. Comparative studies using Sagittarius A-star as a nearby reference improve understanding of the physical mechanisms that govern black hole behavior across mass and luminosity ranges. Through this comparative lens, Sagittarius A-star ceases to be merely the Milky Way's central curiosity. It becomes a benchmark, a reference point by which the universe's most extreme objects can be measured. It stands as both a typical and unique example, quiet yet profound, unassuming yet essential to understanding how black holes of all scales shape the architecture of the cosmos. The Milky Way's bulge, shaped by the black hole At the heart of the Milky Way lies a dense, spheroidal structure of stars, gas, and dust, known as the galactic bulge. Spanning roughly 10,000 light-years in diameter and containing an estimated 10–15% of the galaxy's stellar mass, the bulge forms the central hub of our galaxy. While the spiral arms capture attention with their bright star-forming regions, it is the bulge that reflects the cumulative history of the galaxy. At its center resides Sagittarius A-star, a supermassive black hole whose gravitational pull, tidal forces, and historical energetic events have left an indelible mark on the bulge's structure, chemistry, and stellar dynamics. The stellar population within the bulge is highly diverse, reflecting over 12 billion years of star formation. Ancient stars, known as population 2 stars, dominate, but younger populations exist, formed from gas funneled into the central region over the last few 100 million years. Observations from the Hubble Space Telescope, ESO's Very Large Telescope, and the Keck Observatory show that many stars follow bar-like orbits, elongated paths that trace a triaxial distribution rather than a simple spherical pattern. These orbital geometries are influenced not only by the central black hole, but also by the overall gravitational potential of the bulge and the surrounding galactic disk. Even though Sagittarius A-star directly dominates the inner 2–5 light-years, its gravitational signature indirectly stabilizes the motions of stars across hundreds of light-years, maintaining a coherent bulge structure over cosmic timescales. Gas and dust in the bulge reveal the black hole's subtler influence. Observations of molecular clouds within the inner 500 light-years show high-velocity dispersions of 5,100 kilometers per second and occasional inward streaming motions toward the center. These inflows occasionally feed the nuclear star cluster and historically may have provided material for brief, energetic accretion events onto Sagittarius A-star. Although the black hole is currently quiescent, studies of X-ray emission from Chandra and the Fermi gamma-ray bubbles suggest that roughly 6–10 million years ago, Sagittarius A-star experienced periods of enhanced activity. The resulting high-energy outflows shape surrounding gas, carving cavities, and producing elongated ionized filaments that extend hundreds of light-years above and below the galactic plane. Observations of these structures, including the filamentary radio features known as the radio arc and the northern thread, provide clues to past episodes of black hole-driven feedback in the bulge. The bulge is also chemically unique. Spectroscopic surveys, such as APO-G, Gaia-ESO, and Argos, reveal higher metallicities, particularly in iron, magnesium, calcium, and nickel, compared to the outer disk. This indicates multiple generations of star formation punctuated by supernovae that enriched the interstellar medium. Sagittarius A-star indirectly aids this chemical retention. Its gravitational influence confines gas and dust in the central region, reducing losses to the halo and allowing successive stellar generations to inherit metals from previous ones. This cyclical enrichment has contributed to forming stars like those in the Arches, Quintuplet, and Central Cluster, where metallicity measurements indicate values close to Fe. H is approximately equal to +0.2, slightly higher than the solar neighborhood. Dynamical interactions near the black hole are profound. The nuclear star cluster, packed with more than 10 million stars within a 5-parsec radius, is a theater for extreme gravitational interactions. Stars like S2 illustrate the intense tidal forces at play. Other stars, such as S62 and S4711, approach even closer to the event horizon, with pericenter distances under 100 AU. providing unprecedented tests of general relativity. These interactions can strip stellar envelopes, alter orbital paths, or even eject stars into the outer bulge, producing hypervelocity stars such as HVS-3, traveling over 700 kilometers per second, which may have been accelerated by interactions with the black hole millions of years ago. Modeling these dynamics allows astronomers to reconstruct the gravitational potential of the bulge and understand how Sagittarius A-star contributes to the broader galactic ecosystem. Star formation within the bulge is patchy and influenced by tidal forces from the black hole. Dense molecular clouds near the center experience tidal compression, which can locally trigger star formation, while shearing effects inhibit collapse in other regions. Infrared observations from Spitzer, Sophia, and WISE reveal young stellar clusters embedded within dusty filaments, some less than 10 million years old, juxtaposed against ancient populations exceeding 10 billion years. Massive star-forming regions, such as the Central Molecular Zone, contain over 7 solar masses of molecular gas and are heavily influenced by the bulge's gravitational dynamics. The result is a complex mosaic of stellar ages and distributions, demonstrating the nuanced interplay of gravity, gas dynamics, and stellar evolution. Sagittarius A-star also affects the distribution of dark matter in the bulge. Although invisible, dark matter is inferred from its gravitational influence on stellar velocities. Simulations indicate that the black hole's mass induces adiabatic contraction, increasing central dark matter density and altering the orbital patterns of stars and gas. These changes may stabilize the nuclear star cluster, regulate material inflow, and help maintain the bulge's long-term structural integrity. Models suggest that the central dark matter density could reach 4 solar masses per cubic parsec, substantially higher than in the outer bulge. Observational challenges are significant. Dense stellar populations combined with interstellar dust-obscure visible light, necessitating the use of infrared, radio, and X-ray observations. Data from ALMA, the Very Large Array, Keck, and the Subaru telescope have provided detailed velocity maps, chemical abundances, and gas kinematics, revealing a dynamic bulge with strong evidence of the black hole's indirect influence over scales of hundreds of light years. Even more, gravity on the VLT interferometer has allowed micro-arcsecond scale tracking of stellar orbits near the black hole, providing the most precise mapping of the bulge's gravitational center to date. Sagittarius A-star influences the evolution of the bulge. By retaining gas and metals, it allows continued star formation over billions of years. By influencing stellar orbits and tidal interactions, it affects the bulge's morphology. By interacting with dark matter, it contributes to the stability of central gravitational potentials. The black hole represents roughly 0.01% of the Milky Way's total mass. The Milky Way's bulge exhibits a dynamic structure with chemical enrichment and gravitational shaping. Sagittarius A-star influences stellar orbits, star formation, dark matter distribution, and gas retention. Observations of the bulge allow detailed study of interactions between the supermassive black hole and surrounding stars, gas, and dark matter. The future of Sagittarius A. What lies ahead for our galaxy's core? Sagittarius A-star is far more than a gravitational center. It is a dynamic, evolving entity whose future is intertwined with the fate of the galaxy itself. Though relatively quiescent compared to the luminous active galactic nuclei seen in distant galaxies, the long-term evolution of Sagittarius A-star holds insights into galactic dynamics, stellar evolution, and cosmic processes occurring on timescales that far exceed a human lifetime. Understanding what lies ahead for this central black hole requires examining its accretion potential, stellar interactions, and the broader trajectory of the Milky Way over billions of years. Currently, Sagittarius A-star is one of the smaller supermassive black holes when compared to those in galaxies like M87 or NGC 4889, which exceed 610 billion solar masses. Despite this mass, it is in a low luminosity phase. Observations indicate an accretion rate of approximately 10⁻³ solar masses per year, meaning it consumes roughly the mass of the Sun every 1,000 years. Occasionally, this rate spikes when stellar debris or molecular clouds venture close to the event horizon. X-ray flares observed by the Chandra X-ray Observatory and infrared flares detected by Keck and VLT instruments reveal sudden releases of energy, sometimes increasing the black hole's brightness by factors of hundreds for a few hours. These sporadic events offer a glimpse into the mechanisms that may dominate its behavior over the next millions of years. In the near-term future, spanning the next million years, Sagittarius A-star is expected to maintain this relative dormancy, punctuated by episodic bursts of activity. The central parsec of the galaxy is dense with stars and molecular gas, some of which gradually migrates toward the black hole. The G2 cloud, discovered in 2011 and passing within about 2,000 astronomical units of Sagittarius A-star in 2014, offered a rare natural experiment in black hole feeding. Though it produced only a modest increase in luminosity, the event demonstrated that infalling gas can trigger short-lived accretion episodes. Other dense gas clouds, such as G1 and the more recently observed dusty S-cluster objects, may produce similar flares in the coming centuries or millennia. The black hole's future is also intimately tied to its stellar environment. The nuclear star cluster, extending roughly 5 parsecs from Sagittarius A-star, contains millions of stars, including massive O and B-type stars, less than 10 million years old. As these stars evolve, they will produce supernovae, expelling gas, dust, and stellar remnants into the surrounding region. This material can slowly accrete onto Sagittarius A-star, gradually increasing its mass. Some stars, like the rapidly orbiting stars, may experience tidal disruption events when their elliptical orbits bring them within a few hundred astronomical units of the event horizon. During such events, a star is shredded, with part of its mass consumed by the black hole and part ejected at relativistic speeds, producing luminous bursts in X-ray, ultraviolet, and optical wavelengths. Sagittarius A-star's mass growth will also be influenced by gravitational encounters with other black holes. Stellar mass black holes in the galactic center, numbering perhaps 10,000 or more, may slowly sink toward the central parsec due to dynamical friction, eventually merging with Sagittarius A-star. While each merger adds only a small fraction to the total mass, over billions of years, this process could double or triple the black hole's mass. Observations of gravitational waves from merging black holes by detectors such as LIGO and Virgo provide constraints on these rates, offering insight into the slow but steady mass evolution of supermassive black holes in dense stellar environments. Looking further ahead, the Milky Way's ultimate fate will dramatically influence Sagittarius A-star. In roughly 4–5 billion years, the Milky Way is projected to collide with the Andromeda galaxy M31. Simulations by the Illustris and Fire cosmological projects suggest that galactic mergers funnel enormous quantities of gas and stars toward the central regions, triggering quasar-like activity. During such a merger, Sagittarius A-star could accrete tens of thousands of solar masses over several million years, increasing its luminosity by factors of 10, 410, 5, potentially outshining the combined stellar population of both galaxies. Simultaneously, Andromeda's central black hole, estimated at 4 times 10, 8 solar masses, will also interact gravitationally with Sagittarius A-star, likely forming a binary supermassive black hole system before ultimately merging. This event would release tremendous amounts of energy in gravitational waves, detectable even across intergalactic distances. Even absent a galactic collision, Sagittarius A-star will continue shaping its surroundings. Its gravitational field governs the orbits of stars within the inner 1.5 parsecs, providing a stabilizing influence on the central bulge. By maintaining ordered stellar orbits, it indirectly modulates the inflow of gas, star formation rates, and the chemical evolution of the nuclear region. Long-term observations indicate that over tens of millions of years, this gravitational equilibrium prevents excessive collapse of the central molecular gas clouds, allowing a more gradual and regulated cycle of star formation. Another subtle but significant factor in the black hole's future is its interaction with dark matter. While dark matter cannot be observed directly, simulations suggest that Sagittarius A-star's presence causes adiabatic contraction of the dark matter density profile, gradually increasing central density over billions of years. Estimates place the dark matter density in the innermost parsec at roughly 10, 410, 5 solar masses per cubic parsec, potentially affecting stellar dynamics and the long-term stability of the nuclear star cluster. The black hole's interaction with dark matter may also influence the distribution of compact objects such as neutron stars and stellar mass black holes, concentrating them in the central region and indirectly fueling future tidal interactions. Future observational campaigns will be crucial in monitoring Sagittarius A-star's evolution. The Event Horizon Telescope continues to refine imaging of the black hole's shadow, while next-generation instruments such as Lynx, Athena, and the James Webb Space Telescope will measure accretion flows, flare rates, and the composition of infalling gas with unprecedented sensitivity. Long-term astrometric monitoring of the stars using instruments like gravity provides constraints on relativistic effects, including frame dragging and Schwarzschild precession, offering a rare glimpse into black hole physics that will shape our predictive models for the coming millions of years. Over the next million years, intermittent flares from molecular clouds or tidal disruptions are expected. Over hundreds of millions of years, gradual mass growth through accretion of stellar remnants and gas will continue. Over several billion years, cosmic scale events such as the Milky Way Andromeda merger may trigger quasar-like activity in Sagittarius A-star, affecting the central environment of the galaxy. During quieter phases, Sagittarius A-star's gravity structures the orbits of stars and gas, maintains equilibrium in the central bulge, and influences the chemical evolution of the inner galaxy. Its influence on dark matter and compact object distributions affects the galactic core. Across quiet, active, and merger-induced phases, Sagittarius A-star is the central feature of the Milky Way's nucleus, allowing detailed study of supermassive black hole interactions with their surroundings. Over the coming millennia, Sagittarius A-star will experience small accretion events and episodic bursts of activity, influenced by gas inflows, tidal interactions, and stellar evolution. Over billions of years, quasar-like phases may occur during cosmic-scale events, such as the Milky Way Andromeda merger. These processes will affect the orbits of stars, the distribution of dark matter, and the dynamics of the nuclear region. Black hole jets and galactic feedback. Sagittarius A-star exerts influence far beyond its immediate gravitational pull. Even in its current low-activity state, the black hole participates in a subtle but crucial process known as galactic feedback, a mechanism through which black holes inject energy and momentum into their surroundings, shaping star formation, gas dynamics, and the chemical evolution of their host galaxies. While the dramatic, high-powered jets seen in distant quasars are absent today, Sagittarius A-star still offers a remarkable laboratory for understanding how modest outflows can govern galactic ecosystems over millions of years. Matter, accreting onto a black hole, forms a rotating disk where frictional forces heat gas to millions of degrees. This hot, ionized material can generate relativistic jets, streams of particles traveling close to the speed of light along the black hole's rotational axis. Observations indicate that Sagittarius A-star produces faint, intermittent outflows extending hundreds of light-years from the galactic center. These outflows are far weaker than the powerful jets seen in galaxies like Messier 87 or Centaurus A, which span thousands of light-years and carry energies exceeding 1044 ergs per second, yet their cumulative effects over millennia are significant. The Milky Way's central region is rich in raw star-forming material. The central molecular zone, CMZ, alone spans roughly 600 light-years and contains over 10 million solar masses of molecular hydrogen. Outflows from Sagittarius A-star, even if subtle, can compress pockets of this gas, triggering localized star formation, or conversely, heat and expel material, suppressing it. This balancing act is an example of galactic feedback, a push and pull mechanism affecting star formation rates and the distribution of gas in the galactic core. Evidence of past energetic events provides insight into how feedback has operated historically. The Fermi bubbles, discovered in 2010 with the Fermi Gamma Ray Space Telescope, are two enormous lobes extending roughly 25,000 light-years above and below the Milky Way's plane. Emitting gamma rays and X-rays, they are thought to have formed 6 to 9 million years ago from a sudden release of energy equivalent to 1056 ergs, likely triggered by a brief accretion episode or starburst-driven outflow at Sagittarius A-star. These structures reshaped the interstellar medium in the inner galaxy, redistributing gas and temporarily suppressing star formation in affected regions. Black hole feedback also influences galactic chemistry. Elements such as carbon, oxygen, and iron are produced in supernovae and stellar winds. Outflows from Sagittarius A-star can mix this enriched gas throughout the central kiloparsec, preventing chemical stratification and ensuring a more uniform metallicity in subsequent generations of stars. Studies of metallicity gradients in the CMZ indicate that past feedback events have already contributed to a measurable flattening of elemental abundances, with oxygen to hydrogen ratios around 12 plus log O, H is approximately equal to 8.7, higher than the galactic average in the outer disk. Even modest jets can regulate long-term galactic evolution. Simulations from the illustrious TNG and Eagle projects show that intermittent outflows, like those expected from Sagittarius A-star, maintain the density and temperature of the central gas over tens of thousands of years. These small injections of energy reduce the likelihood of runaway star formation, which could rapidly deplete gas in the nuclear region. Over millions of years, repeated cycles of mild outflows cumulatively affect the structure and evolution of the galactic center. Recent observations provide concrete evidence of ongoing feedback. In 2022, the Atacama Large Millimeter Submillimeter Array, detected high-velocity filaments of molecular gas within 1.5 parsecs of Sagittarius A-star. These structures, moving at speeds of 200–400 kilometers per second, are consistent with small-scale energetic events from the black hole. Meanwhile, the Chandra X-ray Observatory has identified hot gas bubbles within the inner 50 parsecs, with temperatures reaching 10 million Kelvin, likely remnants of previous outbursts. Together, these observations confirm that Sagittarius A-star continues to interact dynamically with its environment, even at relatively low accretion rates of 10⁻³ solar masses per year. Feedback in the Milky Way can be contrasted with more active galaxies. In Messier 87, for instance, the central black hole drives jets extending over 5,000 light-years, directly influencing the intergalactic medium and regulating star formation across the galaxy's core. Sagittarius A-star's outflows are orders of magnitude smaller in energy but serve as a scaled-down model, demonstrating that even low-luminosity black holes contribute to galactic regulation. Studying these processes nearby provides a level of spatial and temporal resolution impossible in distant active galaxies, allowing astronomers to refine universal models of feedback. Sagittarius A-star influences the orbits of stars in the S-cluster and the motion of molecular clouds, while its outflows affect the density and temperature of the interstellar medium. Over millions of years, these interactions impact the Milky Way's central structure, star formation rates, and the distribution of enriched material. Galactic feedback also affects stellar evolution. By controlling the density of molecular clouds, Sagittarius A-star influences where and when massive stars form. These massive stars contribute to subsequent feedback through supernovae and stellar winds, creating cycles that affect the composition, density, and structure of the Milky Way's inner kiloparsec over multiple generations. During the anticipated Milky Way-Andromeda merger in roughly 4 billion years, simulations suggest that gas will be funneled towards central black holes, increasing accretion rates and potentially generating jets similar to those seen in quasars. These outflows could affect the distribution of gas and stars in both galaxies and trigger temporary starburst phases. Observing Sagittarius A-star in its current quiescent state provides a baseline for comparison with future merger-induced activity. Sagittarius A-star, through intermittent jets and modest outflows, affects star formation, redistributes enriched elements, and influences the structure of the galactic center. Although its current activity is subtle, cumulative effects over millions of years impact the host galaxy. Studying Sagittarius A-star and its feedback processes allows scientists to observe interactions between black holes, stars, gas, and dark matter, contributing to models of galaxy evolution. Imaging the Invisible, Event Horizon Telescope. For centuries, black holes existed only as mathematical predictions, inferred from the equations of general relativity. Their defining characteristic, the event horizon, beyond which nothing, not even light, can escape, rendered them invisible to conventional telescopes. Sagittarius A-star, the Milky Way's supermassive black hole, posed an exceptional observational challenge. Its event horizon spans a mere 17 million kilometers, yielding an angular size on the sky of roughly 50 micro-arc-seconds. In practical terms, observing it is akin to imaging a grapefruit resting on the moon from Earth. Capturing such an elusive target required a revolutionary approach, culminating in the creation of the Event Horizon Telescope. Unlike conventional observatories, the EHT is a global array of radio telescopes spanning multiple continents to form an Earth-sized virtual telescope. It employs very long baseline interferometry, a technique in which widely separated radio dishes observe the same source simultaneously. Observatories participating in the EHT include ALMA and APEX in Chile, the Submillimeter Array, SMA, and James Clerk Maxwell Telescope, JCMT in Hawaii, the IRAM 30-meter telescope in Spain, and the South Pole Telescope in Antarctica. By synchronizing these sites with atomic clocks and combining their data with supercomputers, the array achieves a resolution equivalent to a telescope the size of Earth, capable of discerning structures smaller than the orbit of Mercury at the galactic center. The EHT's first major result was the April 2019 image of Messier 87's central black hole. M87 star, located 55 million light-years away, has a mass of roughly 6.5 billion solar masses, and its slower-moving accretion disk allowed a stable ring structure to be captured over several days. Sagittarius A-star, however, presented more challenging conditions. The gas surrounding it orbits at a substantial fraction of light speed, completing rotations in tens of minutes. This rapid variability required the development of new computational techniques capable of accounting for fluctuations on timescales of minutes rather than days. Observations of Sagittarius A-star were conducted during the April 2017 campaign, involving 8 observatories worldwide. The array collected radio waves at a wavelength of 1.3 millimeters, which can penetrate the dense molecular clouds and dust near the galactic center. Over several nights, the telescopes amassed more than 5 petabytes of raw data, equivalent to 5 million gigabytes. The volume was so immense that transferring it electronically was impractical. The data were physically shipped on high-capacity hard drives to central processing centers at the MIT Haystack Observatory in the United States and the Max Planck Institute for Radio Astronomy in Germany. In May 2022, the EHT collaboration revealed the first direct image of Sagittarius A-star. The image displays a bright, asymmetric ring, approximately 50 microarcseconds in diameter, encircling a dark central region representing the black hole's shadow. This silhouette arises from light being trapped or bent by the black hole's extreme gravity, providing one of the clearest observational confirmations of general relativity under such intense conditions. The asymmetry in brightness is caused by relativistic Doppler boosting, where gas moving toward Earth appears brighter than receding material. Modeling suggests that the inner accretion disk rotates at speeds exceeding 10% of the speed of light, generating the observed lopsided glow. Creating this image required not only sophisticated technology, but also extensive collaboration. More than 300 scientists from over 80 institutions contributed, developing software to account for atmospheric turbulence, slight variations in atomic clocks, and rapid variability in the black hole's surroundings. Advanced algorithms, such as regularized maximum likelihood (RML) imaging, were essential for combining fragmented data into a coherent image, effectively reconstructing the dynamic structure of the accretion flow around the event horizon. Measurements of the shadow's size and shape allow astronomers to estimate the mass of Sagittarius A-star at approximately 4.1 plus or minus 0.6 million solar masses. The ring's shape also provides constraints on the black hole's spin and orientation, relevant for studying accretion and potential jet formation. Combined with observations from Chandra X-ray Observatory, ALMA, and VLT, these data support studies of gas and magnetic field behavior under extreme gravity and inform models of black hole accretion and feedback. Future improvements to the EHT promise even greater insights. Planned expansions include adding telescopes in Africa and the Caribbean, increasing baseline coverage and imaging fidelity. Observations at shorter wavelengths, such as 0.87 millimeters, will reduce scattering by interstellar electrons, producing sharper images. These advances may allow astronomers to observe time-resolved changes in the accretion flow, effectively creating movies of matter swirling near the event horizon, and potentially capturing the origin of flares that occur multiple times per day near Sagittarius A-star. Observations of Sagittarius A-star's immediate surroundings provide data relevant to phenomena such as Fermi bubbles, outflows, and episodic accretion events. Combining imaging of the inner accretion disk with X-ray and infrared studies of gas and star formation in the central molecular zone allows astronomers to examine how energy emitted near the event horizon propagates across thousands of light years. The image of Sagittarius A-star provides a direct observational view of the black hole. Its shadow represents the limits of light near the event horizon. The project involved global collaboration, advanced technology, and specialized data analysis to overcome significant observational challenges. The EHT framework is being applied to studies of other supermassive black holes. Efforts include imaging the central black hole of Centaurus A, approximately 12 million light-years away, and the nucleus of NGC 4258, using techniques developed for Sagittarius A-star. Combining VLBI with multi-wavelength campaigns allows astronomers to examine accretion, jet formation, and feedback processes in different environments. Sagittarius A in popular culture. Sagittarius A-star has captured not only the attention of astronomers, but also the imagination of the public. Its defining characteristic, a gravitational pull so extreme that nothing, not even light, can escape, renders it inherently mysterious, making it a powerful symbol in storytelling, art, and media. Over the last several decades, Sagittarius A-star has transcended the realm of theoretical physics to inspire films, television, literature, video games, music, and even fashion, bridging the divide between cutting-edge science and popular imagination. Black holes first entered mainstream consciousness in the mid-20th century, and John Archibald Wheeler, in 1967, popularized the term black hole. Sagittarius A-star became widely known after radio astronomers in the 1970 seconds, including Bruce Ballack and Robert Brown, identified it as a bright, compact source at the galactic center. Sagittarius A-star is located roughly 26,500 light-years from Earth. Its extreme gravity affects nearby stars moving at relativistic speeds. Cinema has represented supermassive black holes in popular media. Christopher Nolan's Interstellar, in 2014, featured the black hole Gargantua, a fictional object whose behavior was modeled using the equations of general relativity. The film consulted Kip Thorne, a Nobel laureate, to depict gravitational lensing, time dilation, and accretion disk dynamics accurately. Gargantua is not Sagittarius A-star, but its portrayal was scientifically grounded. The film's visuals showed light warped around the event horizon and time dilated near the gravity well, illustrating effects predicted by relativity. Television and documentaries have presented Sagittarius A-star in the media. Programs produced by the BBC, National Geographic, PBS, and Discovery Channel, including Nova's Black Hole Apocalypse and National Geographic's Journey to the Center of the Milky Way, have highlighted its discovery, observation techniques, and astrophysical properties. Using X-ray data from Chandra, radio observations from the Very Large Array, and infrared imaging from the Keck Observatory, these programs depict stellar orbits around Sagittarius A-star. For example, the star S2 completes an orbit roughly every 16 years at speeds exceeding 5,000 kilometers per second, illustrating the black hole's gravitational influence on nearby stars. Literature has used black holes as narrative elements. Science fiction novels, from Liu Cixin's The Three-Body Problem series to Kim Stanley Robinson's works, reference galactic centers as locations of high energy or gravitational significance. Authors incorporate Sagittarius A-star's properties, gravitational pull, relativistic accretion flows, and periodic flares into their narratives. Some works, such as the Rendezvous with Rama series, incorporate real astronomical measurements reflecting the scale of the Milky Way's central black hole. Video games simulate environments near Sagittarius A-star. In Elite Dangerous, players can travel to the galactic core, navigating across 25,000 light-years to reach the black hole's location. The simulation includes gravitational physics and relativistic effects. Similarly, the Mass Effect series and No Man's Sky feature black holes as navigational hazards or energy sources. Some games simulate the radiation environment near the event horizon, requiring strategies consistent with real-world physics. Music and visual art have depicted Sagittarius A-star. Electronic and ambient composers, such as Biosphere and Stars of the Lid, use sonic textures inspired by black holes. Visual artists depict spiraling accretion disks, relativistic jets, and galactic nuclei in paintings, digital installations, and sculpture. In 2021, the artist Refik Anadol created a generative art installation using real-time data from the Event Horizon Telescope, simulating dynamic fluctuations near Sagittarius A-star. Educational exhibits at the American Museum of Natural History and the Griffith Observatory combine these artistic interpretations with physical models to communicate astronomical data about black holes. Planetariums, science festivals, and university events feature talks and exhibits about the black hole at the Milky Way's core. The release of the first black hole image of M87 in 2019 and the Sagittarius A-star image in 2022 appeared in publications such as the New York Times, The Guardian, and National Geographic, as well as broadcast segments on CNN, BBC, and NHK. These images were produced by more than 300 scientists across 80 institutions. Schools and informal learning programs worldwide have incorporated the images into lessons on gravity, relativity, and cosmology. Posters, 3D printed models, interactive planetarium maps, and online simulations depict the galactic center, stellar orbits, and the event horizon. Some platforms simulate relativistic effects on time and light. Astronomy apps, including Stellarium and Sky Safari, allow users to locate Sagittarius A-star in real time. Fashion and pop culture merchandise, from t-shirts to enamel pins, incorporate Sagittarius A-star motifs. Sagittarius A-star has measurable properties, mass, location, and accretion behavior that have been referenced in films, literature, games, music, and art. Sagittarius A, key to unlocking the secrets of the cosmos. Sagittarius A-star is not merely a distant curiosity or abstract mathematical entity. It is a dynamic and influential component of our galaxy, and comprehending its nature has far-reaching implications for astronomy, astrophysics, planetary science, and even technology. Beyond being a gravitational anchor, it serves as a natural laboratory for probing extreme physics, a guide for understanding galactic evolution, and a driver of technological innovation. By studying this cosmic powerhouse, scientists can uncover fundamental principles governing matter, energy, and space-time phenomena that cannot be replicated on Earth under laboratory conditions. Sagittarius A dominates the motion of stars within the central parsec of the Milky Way. One of the stars orbiting the black hole, S2, travels at speeds exceeding 5,000 kilometers per second. Observations of such stars provide crucial data to test general relativity. These measurements, including the precession of stellar orbits and gravitational redshift, require precise tracking within milliarc seconds. These details are critical for understanding the gravitational dynamics in the galactic core. Sagittarius A regulates star formation in the galactic center through its interactions with gas and dust. The accretion disk around the black hole reaches temperatures of millions of degrees Kelvin, emitting X-rays, ultraviolet radiation, and sometimes relativistic jets. These processes compress nearby gas clouds, triggering star formation while dispersing gas in other regions. Observations show that Sagittarius A undergoes periodic flare events, lasting from tens of minutes to several hours, with luminosity increasing by factors of up to 10-100 times in X-ray and near-infrared wavelengths. These flares provide insight into magnetohydrodynamic processes and plasma instabilities. Understanding Sagittarius A aids in comparative studies of galaxies. Nearly all large galaxies host central supermassive black holes, and there is a strong correlation between the mass of these black holes and properties of their host galaxies, such as bulge mass and stellar velocity dispersion, the M-sigma relation. Studying the nearest example allows astronomers to calibrate models to infer black hole masses in distant galaxies some billions of light years away. These models inform studies of galaxy formation histories, energetic feedback events, and the role of black holes in shaping cosmic structures. Sagittarius A-star is also a natural laboratory for extreme physics. Near its event horizon, tidal forces stretch matter into elongated structures in a process known as spaghettification, while the intense gravitational field produces extreme time dilation. Temperatures in the innermost regions of the accretion disk reach millions of Kelvin, producing high-energy photons detectable in X-ray and gamma-ray bands. Instruments such as the Chandra X-ray Observatory, the European Space Agency's XMM Newton, and the Event Horizon Telescope have provided high-resolution data on these phenomena. Observations of the inner accretion flow inform models of plasma physics under extreme gravitational and magnetic conditions, which also apply to other compact objects, such as neutron stars, pulsars, and distant quasars. Technological advancements developed to study Sagittarius A have impacted multiple fields. Techniques like very long baseline interferometry, adaptive optics, and high-resolution spectroscopy allow precise measurements of stellar motions, galaxy imaging, and detection of faint cosmic signals. VLBI synchronizes radio telescopes across continents, creating a telescope with an aperture the size of the Earth, allowing angular resolutions of tens of micro-arcseconds. Such precision has applications in geodesy, satellite navigation, communications, and Earth observation. Studying Sagittarius A-star also contributes to our understanding of habitability and planetary system formation. Supermassive black holes shape the distribution of gas and dust in galaxies, regulating star formation and dispersing heavy elements required for planet formation. By comparing the Milky Way's central region to other galactic nuclei, astronomers can assess how black holes influence the potential for habitable zones, the frequency of stellar flares, and the radiation environment experienced by nascent planetary systems. Such research helps refine models of where life-supporting planets might emerge and survive over billions of years, extending our knowledge of cosmic habitability. The public and educational impact of studying Sagittarius A-star cannot be overstated. Images and videos from telescopes, simulations of stellar orbits, and flares have captured global attention. Outreach initiatives use these discoveries to inspire curiosity, demonstrate the scientific method, and foster interest in STEM careers. Programs such as the International Year of Astronomy in 2009 and the Event Horizon Telescope public lectures have exposed millions of students to cutting-edge astrophysics, linking the study of the Milky Way's central black hole to broader educational goals. Understanding Sagittarius A is essential for space exploration efforts. Knowledge of gravitational dynamics, radiation hazards, and high-energy phenomena near supermassive black holes is critical for planning missions to distant regions of the solar system and beyond. Monitoring stellar orbits, flare frequency, and the distribution of gas and magnetic fields around Sagittarius A provides important data for navigation and mission planning. While crewed missions to the galactic center are not currently feasible, ongoing simulations and theoretical studies are developing the necessary groundwork for future space exploration. Sagittarius A plays a critical role in understanding galactic dynamics, high-energy physics, and star formation. Its study contributes to advancements in technology, planetary science, and space exploration. Research into the extreme environment surrounding the galaxy's central black hole provides insights into fundamental physical forces and processes that have shaped the Milky Way.